Often in hydraulic circuits, we have multiple components that are hooked up in series or in parallel. So what we'll talk about today in this lecture is how to create equivalent resistances for multiple valves that we might have in series or parallel configurations. So first of all, we had talked about how we created the orifice equation from Bernoulli's equation, and again we have in this case a knife edge orifice where we have a constriction in the flow path, and as that constriction obstructs the flow, we have a pressure drop across the orifice. And again, what you see on the right side of your screen is the orifice equation. So let's now apply that to a hydraulic circuit. So this is a very simple hydraulic circuit. It doesn't actually do any useful work, but we have a hydraulic pump, and the hydraulic pump has flow that is going through right here a needle valve, and then coming down through the needle valve we have a flow meter where we're able to measure the flow, and because we have two pressure transducers, we can look at the pressure differential across the valve related to the flow that would be going through it. So because of this orifice equation, we have a relationship between the pressure drop and the flow rate. And so let's say that my pump here is creating maybe a flow of, let's say, 4 liters per minute. Well, for that given flow rate, which might be right here of 4 liters per minute, I can move across and find for that given flow rate, here would be the pressure drop that I have. And if I was to change the area of my valve, I could change what that curve looks like and therefore change what the pressure drop would be for that given area. Now, what I'm going to do is I'm going to take this orifice equation and I'm going to lump a few terms. The terms that I'm going to lump here are the discharge coefficient, the area of the valve, and this rho over 2, the square root of that. I'm going to lump those those 4 terms and call this a K value. And so my purpose in doing this is just so that I can represent those without having to break them down and try to figure out what each one was, because the discharge coefficient is a function of what type of orifice we have. The area of the valve is usually difficult to measure, and then we have a density of the fluid, which is usually constant or hopefully constant across the range that we're operating. So I'm going to take this information for a single valve and now apply it to multiple valves. So let's first of all look at the case where we have valves in parallel. So it would be saying that valves or flow is being split between these two valves, just like in that circuit right there. And the first thing that you'll note is that the pressure drop across both valves is the same. So from pressure 1 to pressure 2, we have the same pressure differential. And if these are ideal flow meters in this case, they are not contributing to an additional resistance in the system. But there are different flows going across those two valves. And so if I look at that same pressure drop versus flow rate plot, now I can say I have N1, which would be for needle valve 1, and N2 for needle valve 2. I have two different orifice equations, or coefficients of my orifice equations, that create these two different plots. The combination of those two will add up to this equivalent. So again, I have the same pressure differential across those. So if I am right here with the pressure differential, then I could move straight up from there and say this would be the flow rate moving through valve 1, this would be the flow rate moving through valve 2, and the entire flow rate would be this one right here, which would be the entire pump flow. So that might be the 4 liters per minute. So what I want to do is come up with an equivalent needle valve for those two valves that are in parallel. So I'm first of all going to take these two orifice equations, one for needle valve 1, the second for needle valve 2. And again, I have the same pressure drop across these valves. So I can say that the total flow rate between these valves is Q1 plus Q2. I then am going to substitute in the orifice equations for both of those. And so I have K1 and K2, again describing the resistance of valve 1 and valve 2. And then I just collect some terms here, and I have this K1 plus K2. Well, this term right here, this is my K equivalent. So now I can take these two valves, put them together, and create this equivalence. Now, if you've taken an electrical circuits class, you might say, well, this looks familiar, but this was the equation we had when we had resistors in series. But now we're applying it to hydraulic valves in parallel. Well, why is that? Let me take a quick detour here to just a comparison between electrical circuits and hydraulic circuits. Where in electrical circuits, the way we define a resistance is looking at the voltage and saying that's equal to the current times the resistance. So if we look at these variables here, this voltage, this is what we refer to as an effort variable. Our flow rate here, or our current, I should say, is a flow variable. And finally, R here is a resistance. Now, if you jump over to the hydraulic domain, where I have a similar equation, but now you notice that our effort and flow variables are in different sides of the equation. So we're really defining our resistance slightly differently, where I've got Q being the flow variable, I've got the pressure differential being my effort variable, and the resistance being this K right here. So we have simply defined our resistance in a different way in the hydraulic domain than what we did in the electrical domain. The other thing that you'll notice between these two is that our hydraulic resistance is nonlinear. And this is why hydraulic components or hydraulic circuits are a little bit more difficult to analyze, because they are nonlinear. And we'll see that more later on in the course. So we take these two series resistors, we put them together, and we just add them up to create the equivalent resistance. But the hydraulic domain, we take two orifices and have them in parallel, and we can just add up their equivalent resistance. So again, they are similar, but because we've defined the resistances differently, we have to treat them differently. All right, now what if I take these two valves, and instead of having them in parallel, what if I put them in series, connect one to the other? Now, each valve sees a different pressure differential, but they share the same flow rate. So I can create these similar curves here, and now because both of these valves are sharing the same flow rate, I might be at a flow rate right here, and as I move across, I can see that the first valve, or valve 1, would be having this pressure differential, and valve 2 might be having this pressure differential across it. We add those up and we have the entire pressure drop of the system. So again, I'm going to start off with my orifice equations for both valves. I'm going to rearrange these now in terms of the pressure drop across each valve. So valve 1 would be seeing pressure differential from pressure transducer 1 to 2, valve 2 from 2 to 3. Now I'll say that my total pressure drop across the two valves to create an equivalence is pressure 1 minus pressure 3, and create this form P1 minus P2 plus P2 minus P3. One step farther, now I substitute back in these terms that I had up here, P1 minus P2 and P2 minus P3. I substitute those in, and I can say that here would be my equivalent orifice, and now I've got this being the equivalent of that. Now, you'll notice that I've got K equivalent squared in the denominator, so if I want truly K equivalent, I have to rearrange this just a little bit more, and then I have this equation that's on the bottom here. So this would be the equivalent of two hydraulic resistances, orifices in this case, in series. A little bit more complicated than the parallel, but the methods are very similar, just a little bit more math to it. So in closing, in the case where I have two valves in parallel, I simply add up their effective resistances to create an equivalent. When I have them in series, it's a little bit more complicated, but they share the same flow rate, have different pressure drops across the two of them. Now, the method that I proposed here, that I've shown here, is applicable to these orifices, but also other types of hydraulic loads, like a pipe flow resistance or motors, but we just have to come up with slightly different ways of expressing these based on what the load type is. Thank you.